Good afternoon, judges. We are Team Imagine Losing, and we will be tackling Team 1 for Code Sprint. In line with Team 1, our project addresses port congestion, a major challenge that threatens the resilience of port operations. At Port of Singapore, roughly 90% of container ships arrive later than scheduled. This contributes significantly to vessel congestion, averaging around 2 to 3 days of wait time just to berth a ship. Resilience is built from within, and hence we focus on optimizing port traffic flow and resource allocation to reduce bottlenecks. For our project, live AIS data is fed into the ETA model, which processes real-time vessel movement. AIS will give us information about each vessel, namely its coordinates, dimensions, heading, and draft. On the other hand, the waiting time model is trained on intrinsic characteristics of the berth, such as current usage, dimensions, draft, day, and season. Now, given these two predicted values, we can find out which berth has the lowest waiting time, and hence the turnaround time, for a ship to be routed to. A greedy heuristic gives us a locally optimal solution at each decision point, allowing us to find the berth with the lowest waiting time.
So when they come to the dashboard, they are greeted with a live AIS monitoring system, which will show them the movement of vessels within 12-kilometer radius of the port of choice, in this case the port of Miami. On the right side, we also see the estimated time of arrival of each ships, which is trained and predicted based on information of the ship or vessel, such as latitude, longitude, SOG, COG, etc. When users wish to do so, they can refresh the ETA to see the live and new updated time of arrival for each of the ships within the radius. Furthermore, users can select on the ship to see a recommended berth for that specific ship. This is predicted using features such as the length of the ship, the season of the ship, the type of the vessel, etc. We are also providing them with an estimated waiting time to know how long they have to wait before being serviced at the specific berth.
So we're looking at our ETA model training, and we can see that we have taken data set from the AIS. It's the 2019 to 2022 AIS data set, which includes hundreds of thousands of data sets. And after pre-processing and training on these data, which includes latitude, longitude, SOG, which is just speed over ground, and cost over ground, heading, vessel type, and so on and so forth, what we found is that there are two key features, in fact, that will enable us to determine our Y value time to port, and that is the distance to port and the speed over ground, latitude, and width. So what you'll see here is that for our model, as we trained it and tested it, we find that the best way to optimize our model was using k nearest neighbor, with the R squared, MAE, and RMSE the most optimal. You can see here, this is where our MAE and RMSE is plotted against the different models. For our WT model training, what is happening is that we've taken and extracted data from many various sources, and we have had up to 10,000 rows of data. After processing, we have cut it down to about 1,000 to 2,000, 1,900, 1,000 rows of data. Feature types like ship features, temporal features, berth operational features, berth generic features. These are features that we have taken into account from various sources like Baltic Shipping, Port of Hong Kong, and so on and so forth. And what this helps us do is that from this data source, we're able to tell how long ships have docked at the Port of Hong Kong. And we were able to mathematically compute things like berth delay, ships in port based on the data available, the even details about the berth in general, like the berth max draft, the berth's max length overall, berth length. So what happens then is that we're trying to predict the port waiting time, and you can see here that the Port of Hong Kong actually has their own expected waiting time derived, and we'll show why in later slides why our model is more powerful than theirs. So how we did it was we collected and filtered the data from various sources. We trained it using for predicting things like ETA, and for predicting things like the lowest waiting time. And then we utilize industry standard evaluation matrix to gauge model performance. And you can see that for WT model, we have found that our model compared to the Hong Kong port model, when compared with the actual waiting time that ships have actually spent, the R squared is 0.64 hours, whereas it's negative 0.07. And as you can see for MAE and RMSE, we are much lower than the Hong Kong ports estimated time of departure or expected waiting time. And these were the techniques that were employed. We had k-fold cross validation over 1.2k dataset, and we use XGBoost regression along with a grid search CV to find the best parameters as listed here. You can see that there are some outliers in our data. We are computing predicted waiting time, and we're comparing against actual waiting time. Expected waiting time is the waiting time that Hong Kong has, and you can see that there is some outliers in our data, but apart from that, those outliers on a case-to-case basis, our model often uh, is much better than the expected waiting time than the Hong Kong ports model. For the tech stack, we are using Next.js with TypeScript. For the backend, Flask and MongoDB, and for AI technologies to train our data, we're using sklearn and XGBoost. Thank you.